Okay, last time we talked about how to derive this equation right here, which is the most general type of equation for describing behavior of pollutant in the water. So that includes dispersion, advection, and reaction. So this one has virtually everything. And to understand the system better, last time we studied about steady state. And by let this one be 0, and then we can assume my equation, my solution for C can be like this. And also, if you have boundary condition like that, and then you can back calculate F and G. So, and also I said that this is not just something that we must have all the time. This is not the case. This is just one of the sample. Okay, so this is not something we just have to have it all the time. But pretty good assumption for a general case if you don't have anything. And in here, we also talked about some very special case, which is Asteroid case. In that case, we have actually 3 boundary conditions. And we have 0 for minus infinity, 0 for plus infinity, and C equals C0 at x equals 0. So we have 3 boundary conditions, and because we wanted to calculate 2 unknowns, and if we have 3 equations, we are in trouble. So we want to differentiate 2 by case for 2 unknowns and 2 equations, and 2 unknowns, 2 equations. So we'll separate situation, assuming we are going to have different solution in this case and that case, right? So we have we can calculate, we can come to the conclusion that we can have different lambda for different sign of x, and so we have that kind of equations. Okay, Picklin number and non-polar number. That's if you were chemical engineer, and I think you would you will find this kind of equation very often. But this number, and this would indicate, when this number, this is a number, does not have any dimension. In other words, if you have Picklin number, which is L, U, and E, if you take a look at their unit, we can find they all get cancelled. In other words, this one has no unit. No unit, and this is just number. So we call this as dimensionless number. Number that has without any dimension. This one gives us a lot of freedom. Okay. Sometimes many times we find, and some textbook use feet, pound, but many times we also find other books use meter and gram. And feet pound is called as English unit, even though nobody in England uses it. But anyway, that's the one that is being used in US or America, which we don't really understand. But European countries, they use SI unit. Okay, for Dongil number, if that is defined as k, which is 1 per, let's say, let's just use the same, try to keep the similar expression. Okay, if you take a look at this one, also we also find we can cancel their unit. So this one also is the dimensionless number. Okay, dimensionless number without dimension. Okay. So if we use this kind of thing, we are safe. No matter what kind of dimension that you use, we are just gonna find. So this is very good. And if we think about their meaning in here is, they have velocity and dispersion. And if numerator is big, that means we have big velocity. If denominator is big, it means we have big dispersion number. If PE is big, P is, let's say, I don't have, no, maybe, let's say 100. In other words, if this is big number, then you can dominate. In other words, we can maybe ignore this person in that case. So if we have a big particular number, that means they're very fast river. Okay? Very fast river. In that case, the movement of water is dominant factor to carry your wood. Another term is Dongil number, and that is K versus U. That is decay and velocity. Okay? If you have a big Dongil number, that means you have a big decay. And if you have a very small Dongil number, then you have very small decay. So, and we had general equation like this, okay? And if we convert our equation from that by using this expression, we can convert this to this equation like here. Okay? And how we do that? That's a matter of definition of differential equation. Okay? If we have x prime equals x over L. This is also a dimensionless number. Okay? And C prime is C divided by C in. Okay, this is the original concentration. Let's do this. I will do this, and then C equals then C in times C star. Okay, and in here dc dx is C in C dc star dx, right? In this case, dx is L dx star. And what I want is dc star divided by dx star, right? So I need to replace my dx in here. So, and I will just keep writing. And if we replace dx with that, and then this is L and dc dx like that. Okay? Right? So and I can actually replace, let me just copy the equation from here. Yeah, I'll just cut this one. Right? So I can actually replace that term to here. Okay? And C in here can be replaced with that. But still we have some problem with this one. Okay? We don't have this one yet. But also this one is actually dc dx, x plus delta x, dc dx, and x, and divide by dx, right? Okay? And we now know we can replace this one right there and right there. And then we can replace this one right there. Okay? So it's very easy to replace this one as well. So I want you to, I intentionally just use the arrow so that you can use your brain. So I want you to use this and this kind of process and to come up with this one, right? By this Wednesday, you should drive. By using this one, you need to replace stuff, and then you get to come to this conclusion. Okay? And then, if I just keep going on, CINL, DC star, EX star, and let me just x plus delta x, and in here dx is L, dx is star, right? And so we can have what is this? Probably like something like that. So if you can replace this term to here and then play with that, you will come to this part. So, and if you plug in everything and you will come to this kind of stuff, and then we will, if you compare this and that, you can say, okay, this one is the same as Dongil number, and this one is the inverse of Piclet number. Okay? So I want you to try to memorize the name of those term, Piclet number, Dongil number. And Piclet number actually is going to be used a lot if you are in this river analysis business. And Piclet number is very much important. And when you are an environmental engineer, you need to know how to communicate with people, with the civil engineering people. And also you need to know how to communicate with the chemical engineering people. You need to know how to communicate with biological people. You need to know how to communicate with government officers. Everywhere, everybody. So, what is environment? Environment is everything, right? Okay, we now have another number which is called as asteroid number, and this one compares dispersion and velocity. As you can easily imagine, their unit can be cancelled each other. So this one can be another Imagine that number. So if we have 0, that means we don't have any dispersion. If we have this very big number right there, and then you have a very big dispersion. So people use those three numbers to divide the situation. And when you deal with the data and rivers and lakes and estuaries and even oceans, and it's very confusing when you play with the data. And you somehow have to, what we want to say, okay, this is this case and then that case, but how do you do that? And we have some kind of standard, right? If we use Kirkland number, if we use Dongil number, if we use Asteroid number, then you can divide groups this and like that, and then you can say, okay, from here dispersion is dominant, from here velocity is dominant, from here decay is dominant. So we can separate those groups. So that's very important. Very important. When you write papers, when you write reports, and you need to somehow use the tools that you can use mechanically, okay? Then that kind of things make your life a lot easier. Okay, so and in this case, if this one is called eta, and it says if this is bigger than 1, dispersion is big, and less than 1, diffraction is big, and but to be safe, if this is bigger than 10, really big dispersion, less than 0.1, really big diffraction. Okay. So we can use some example, and in this case, when you call ratio also is a dimensionless number, and let's say I think this one is the same as this one, ratio P, because I got those from different textbooks, and so far what I have said was Ke by U, and lambda in general, lambda is the solution like that, and this P, it can be defined like this, and this one also is very similar to the Asteroid number before, except at this part. Well, anyway, we can use it. You don't have to memorize those numbers, 0.05, 0.1, whatever, but you know those meanings when you look at this. Okay, it's going to be better to have a look at example rather than explaining those small numbers. Okay, you have a decay rate. It is very big anyway, and this 0.5 is way big. Anyway, and if you have 0.5, that's the property of your pollutant. Let's say you have a BOD. Decay rate is 0.5 per day. That's the assumption. And in river, you have rivers in river part, and you have bigger velocity. Let's say we have 10 miles per day. Mile is about 1.6 kilometers, by the way. So, and this is 1. And dispersion number, obviously, in asteroid situation, we have bigger dispersion number, which is 10 and 1. And these are just calculations of those numbers, so you don't have to really care about that. And lambda in here was, one is plus, right? The other is minus. The plus is this one, and lambda minus is this one. I hope I'm right. Okay. And then if you know this burden number, we can calculate the asteroid number, which was eta. And k divided by u is like that. Also, p in this case was defined like that. Okay, so we have many numbers, but anyway, and in here lambda, if you compare this lambda, one is 0.0249, almost lambda, probably there is, okay, lambda, okay. And in this case, we are going to just think about plus term only, okay? And then 0.025 is for river. And lambda for estuary is 0.116, which is a lot bigger, right? Okay. So this one is trying to compare this one, and in the string, and k divided by u is 0.025 and 0.025 right here. And what is k divided by u? And when we have plug flow system, and if we don't consider dispersion, and we can have something like this. This is very similar to, if you remember, okay? Because we know this one is, if we have constant velocity, and constant velocity is defined by, like this, the distance divided by time. And this t is the time required to move from A to B, okay? And also we can, I want to differentiate this one. If we are in batch system, we often use this kind of graph and then come up with, okay, C minus C equals C minus KT. In this case, my T is your time. Of course, this can be your time as well, but the definition of this one is this moving time from A to B. So, and in this case, for time now, it's a little bit confusing, so we can just select it. But the internal meaning of this one is the same as T. So we will use this part to compare, because we know our Asteroid system, we have lambda x, right? So we have two different systems. Okay. And I think this one can be minus as well, okay? Because this and that should be in the same direction. Okay. What this one says is between this lambda and this one, there is not so much difference. Okay. They are different about 0.0001, right? So it means you can use this, you can use that, either or that, no problem. No problem. So if those are not too much different, why do we have to use the complicator? We'll just forget about this. Okay? So in that case, you can just ignore this burden. So in the string situation, we don't care about this burden, okay? Because this velocity is fast enough to move the stuff. But in the case of estuary, K over U is point, what is this? Point, this must be point, okay, U is now different. U is now different, okay? U was 10, but now it's 1, so U is, this is wrong, this is wrong, also that should be point, two five, right? So in this case, K over U is 0.25 and lambda is 0.116. We can say they are not similar, they are different. So in that case, in Asteroid, we have to use, you have to consider dispersion equation. So in that case, if you want to compare this and that, then this kind of stuff is something that you want to use. Asteroid number is like that. Okay, if asteroid number is small, then okay, we can ignore dispersion number big. We have to consider. Okay. So I just said compare this lambda and K over U, and the original meaning of those was the exponential, the power term, right? So you know now those meanings. Okay. And steady state solution is like that, and for asteroid we have a solution like that, and we now know lambda is that. And at this time, I want to think about how do we calculate C0. Well, if we are given as your measured data, and then it's going to be the best. But sometimes you just have to calculate C0. And since data are not so much abundant as I wanted always. Okay. In this case, so then we will assume some kind of situation. We have a sandwich again in here, and we'll think about just one line, which is -0 this way and +0 this way. -0 +0. Okay. Actually, this is the line. I just exaggerated to show you the situation. So we will develop a mass balance equation for this little piece, and so we have something coming in through advection, AUC or QC, and QC we have x at 0 minus place and x 0 plus place. Okay, so this is coming in and this is going out. Okay, you get dispersion right here coming in, dispersion going out, and we have in this little space we have decay, and in here we now know we have some input from a factory or the treatment plant or tributaries whatsoever. Okay, and then we will try to simplify this situation. In this case, because this is line, my delta V is going to be 0. Since this is line, just line. Okay? Because I'm talking about plus and minus 0. So we will ignore this part. Okay? No volume. And in here, AUC, plus 0 minus 0. If A is the same, U is the same, I think C is almost the same. Right? So we'll just disregard this and that. So we are left with this, and that. 3 terms. 1, 2, 3. Okay? And then we know we have C equals C0 lambda x for plus situation and minus situation. So we have one for minus and the other for plus. And for minus case, and round C, round x is C0 lambda E and lambda x, right? If we differentiate this one, we can say like that. So we have round this round x in here, and round this C round x there. And one is for x equals minus, and that one is, I think, probably, and lambda 2 is minus. And you can say either way, and this is always confusing, but as long as you keep the same directions all the time, you have no problem. Okay? In other words, we can just cancel everything, and in here, lambda 1 is, okay. What is lambda, by the way? Lambda is 2e u plus minus root so like that, right? And this is 2e over u plus minus root maybe okay. Anyway, if you one is lambda and lambda 1, the other is lambda 2, lambda minus lambda 2 in here I will have lambda 1, which is plus, and the other is lambda 2. Then you can actually cancel this part and double this part. Okay? So if you substitute that one to here, you have a cancel the plus, the front part got cancelled, and second part got doubled, and then we can have things like this. Now W is equal to this one, and what I wanted was I want to calculate C0, right? So I can back calculate C0 by using this relationship like this. Okay? So what you have to do by Wednesday, another day, in addition to pick a number and download the number of digits, and you need to submit how to derive C0, okay, from that equation. Okay, rest of the part are easy, and if I have velocity u 0, then this is 0, then that is 0, which is very simple. Okay, but when you deal with this kind of equation, you need to be very much careful. When you have lambda like this, when you have u equals 0, then it's going to be easy for you to say, okay, I have 0 plus minus 0 plus 4ke, and then plus minus e root ke can be something that I wanted, maybe Okay? Fortunately, this time we have just the one same equation. And if you know your C0, let's say you had a C0 right there, and you can actually substitute 0 to here, and then maybe in this case you can put u to here, and then you can have a different u. But in this case, you cannot substitute 0 in here. Okay, so sometimes you will get puzzled. So in that way, the most general way is you go back to the original equation and then cancel u and start all over from here. Okay? When u is 0, you can use that one. When k is 0, then you can use that one. Okay? Okay, and then let's think about the meaning of those. When u equals 0, okay? When you have a 0 situation, and then we now know in this asteroid, when you have C0, and your general equation is like that. And because we have velocity moving to here, and dispersion actually moving out of the system, because this one is has a higher concentration, and the outside have lower concentration. So my concentration always want to move outward. Okay? So we have some kind of cancelled effect in here. So I have a kind of very depressed situation, and this one is a little bit exaggerated situation. Okay, so we have plus minus effect together, so they got cancelled, but we have all the plus effect at the same time, so they have kind of added effect, right? That's because of u. If you have I don't know if those are the same enough. If u is 0, then you will have same dispersion there. Then you must have the very nice looking symmetric, right, shape of the curve. So this way, I think this is almost the same. Anyway, so because this one is a little bit cancel the effect, but because you don't have any velocity effect, so the dispersion this way and that way must be the same. So, in other words, my C equals C0 E lambda x. In this case, I have something is one is plus minus k over E is x. So, accepted sign plus and minus, the absolute value of my expressor term is the same. Okay? So that's the meaning of this situation. And then if you want calculate C0, and you also have to go back to this original equation, and then probably maybe we can just ignore. Well, you can do that. Maybe we are tempted to do it somewhere in the middle of there, but that's not actually the perfect case. And actually, you have to go really back to the original situation and then try to come from there. So if we calculate this one, and we can have situation like that, and also if we have zero situation and k is zero situation, then in this case we have a and in this case, I guess we'll have this kind of situation, and then my lambda is going to have that. My one lambda is 0, the other lambda is u over lambda. Okay? So this one says if I have a zero situation and I have a c equals c0 e lambda x, and for a plus case I have to use this one. For minus case I have to use this one. So my minus is like that, and then since my c equals c0 e lambda x, and my since lambda is 0, and then I have the c0 situation. This is just ideal case. Yeah, mathematically, yes. In reality, I don't know. But this one says since I have no decay means just constant, right? So since this one is 0, simply this is 1. Mathematically, this is like that. And you can say, whoa, what are you talking about? Can this kind of thing happen? Yes, you're right. This is going to be impossible. But by this expression, mathematically, it's okay. Mathematically, okay? So this one says, if you have some ocean and you have a salt concentration, salinity, and if you have very constant salinity, let's say 0.3%, okay? 3%? 3%, yes, 3%. And then, well, actually the salt concentration or salinity, they are different. Because if they are closer to the land and their concentration low, if they are away from the land, their concentration can be constant. So we have to go a bit of distance to find a steady state anyway, and this is the situation like that. Okay. And what if we have multiple sources? We have a river coming in and another river coming in. And then what are you going to do? In that case, we have a blue curve and we also have red curve. And eventually, if you have two situations, then the total effect is going to be summation of those two. So when we think about blue curve only, blue curve right here. In here is this, we're talking about 1, and we will just ignore this part. And from here, we have C0 and e to the lambda x somehow, right here. And we don't care about this. And from to there, we have a lambda 2 situation. So no problem, okay? From here, just like that, if we ignore this part, and x minus L, we'll take care of that later. But anyway, from here, we will think about all the way from here is about lambda 1. This is L, by the way. And from L, and then we have lambda 2 situation. Then, the only thing that I care about now is distance. So I have no problem with this part, because I can just use plus x minus x. In here, this one is where? This one is distance L. Okay, distance L. So if you are at L, if you x equal L, that means in here for dash C0 for this situation. Right? If you substitute L in here, this is 0. Then this is 0 too. Okay? So from here, you have distance x minus L. X minus L. So this must be the distance from there. X minus, that's what it is. And for the same, and we have the same situation for the minus case. So added effect is additional boost. Think about it. Think about it. Okay? And if that's something you have learned in your high school before, I guess, because when you move the stuff from here to there, and then you have a minus something, right? And this is simply the movement of this figure from here to there, and then we'll just add the stuff. Okay? Alright, and then we are about this much. We'll just practice this one again, and then chapter 9 has a lot of stuff. A lot of stuff, but I'm not going to cover everything. I just put a lot of stuff. And if you have printed out, you can also actually find